We're going to start talking about a few more derivatives. Before you leave today, you're going to have 6 new derivatives in your life. Okay. So let's start by thinking about sine inverse of x. We're going to derive from first principles the derivative of the inverse sine. That is arc sine. You know, we've graphed this at the beginning of the year. Here's sine x, and there's arc sine in red. And I think you can maybe even guess that this might be our move, given that we've just been talking about implicit differentiation. Why would we like insert a conversation about implicit differentiation before moving on with more of our derivatives? Well, I think it suggests an interesting way to do this. I don't know the derivative of sine inverse of x, but I do know the derivative of sine, and maybe that could help, right? Because in this equation, y equals sine inverse of x equal, at least for a certain set of values, sine y equals x. Can't we just use the fact that these are inverses to our advantage? And sine y of x equals x. I do know how to differentiate that, don't I? So here's something I don't know how to do. Here's something I do know how to do. This is like, well, this is the business of mathematicians, right? It's like take stuff we don't know and see if we can recycle things we've done before. So using implicit differentiation on the left side, you get, if you take derivatives on left and right, you get cosine y times dy dx, don't forget the chain rule, equals, equals 1, but thanks for participating. And so I think we've like done it. And so, well, we're not completely done. I think we can do a little better, but we have dy dx is equal to 1 over cosine y. We solve for dy dx in the fashion that we've been doing lately, right? But I still like, if I can, I'd love to get this in terms of x. Like I'd love an explicit formula in terms of x. So that's what we're about to do now. You'll remember maybe from pre-calculus that another way of talking about cosine y, this comes from the trig guidance. Now we need to worry about like the plus or minus maybe a little bit, but do you remember that like 1 minus sine squared is cosine squared? So if that's true, then we could re-express this denominator. You might be thinking, why would we want to do that? But trust me, let's re-express this denominator as the square root of 1 minus sine squared. And if we're on this, again, we need to like consider the fact that we're on a limited domain or range, depending on which function you're talking about. So we'll just take the positive square root because of that. Then we get the following. So like I said, cosine y is equal to the square root of 1 minus sine squared y. And sine squared of y is x squared? Why? Why is sine y? Is sine y just x? Yes. Oh, yeah, it is. By like definition at the beginning, right? So you see how that worked? Very nice, isn't it? Because in the end, you kind of think, wow, I expected something like trig feeling. But actually, the derivative of arc sine is this nice algebraic function, 1 over the square root of 1 minus x squared. And you just saw the derivation. Feels very similar to derive all the other arc trig functions. I think when we're done with it. Are we done? I have the schedule over here. I just want to make sure we have it. I'm about to make a choice whether we have 210. Okay. I was trying to think whether we want to derive some of the other ones here or not. Oh, we'll keep going here. 210. Yeah. We'll keep going, but I'd love to come back and maybe I'd love to derive this in another way too. That's kind of nice using triangles. So there's a new derivative for us. The derivative of arc sine is 1 over root 1 minus x squared. And yeah, on the next page I'll give you all 6 arc trig function derivatives. I will just draw it off to the side because it's pretty quick. The other way that you might like to do this too, which will remind me maybe of a task you might have done in pre-calculus, if you're trying to figure out this, cosine of sine x. Isn't that what we have here? Isn't this cosine of sine x? Right? Isn't y sine, excuse me, did I say that wrong? Sine inverse of x. Just from the original. How do we reconcile this expression? Is there a way to do that without having to resort to the trig identities? Here's a little picture. Remember, sine inverse of x, that means an angle that has a sine of x. I think I can draw myself an angle that has a sine of x. Right? Doesn't that angle have a sine of x? What's the cosine of the angle that has a sine of x? Right? So that's, I mean, both are this is, what did you just use to figure that out? The Pythagorean theorem. Well, what is this called? I forget. Oh yeah, that's right. It's called the Pythagorean identity. I mean, they're derived from the same, it's the same math. I just kind of like the picture to help me figure out why is 1 over cosine of sine inverse, why is that 1 over root 1 minus x squared? I usually draw myself that little picture over there if I forget. So there are two more, excuse me. And again, if we might have time, I might encourage us to derive a couple of these. This one's not too bad. This one's a little strange. Tan inverse feels very much the same though, in terms of how you derive it, using the same idea as what we just did. In all cases, you'll do implicit differentiation if you're trying to derive these from first principles. And then the reason I'm putting these separately is because I need to convince you, if you haven't heard of this identity before, I need to convince you that this is true. At the very least, at the very beginning of the year, do you remember this? You actually graphed some of the arc trig functions. Do you remember graphing arc sine? It was like first week of school, maybe third day's homework on the review week. And I had you graph sine inverse and cosine inverse. And at the very least, maybe you remember that sine inverse and cosine inverse are just vertical shifts and a flip of each other. Oh, I can draw them off to the side here. Sine inverse looks something like this, right? Make sure I get it right. Cosine inverse looks something like this. Yeah? I mean, that's not a full argument, but it's certainly true that they are the same graph, actually. Just one is what set of transformations transforms one into the other. Well, how about take this graph, sine inverse, and flip it, and then move it up by pi over 2 units. If somehow I can convince you that sine inverse and cosine inverse are just a reflection and a translation of each other, can you tell me what the derivative of cosine inverse is? Well, if it has this relationship to sine inverse, then it's just the same thing except with a negative out front, right? Because the pi over 2, take the derivative of that doesn't matter. It's just a translation up and down, doesn't matter. And the negative will reverse all the answers. So, and that's true of all of these. So, in fact, there's not any reason for you to, like, if you're into memorizing things, memorize these, but don't memorize these. There's no reason to do that. So all the notice that I mentioned it here as the cofunction derivatives. Right? If you put a co in front of any of those, you get the negative of those. Okay. The opposite of those. I have to maybe explain why that's absolute value of x, but besides that, and then now I need to figure out what tan inverse is. I just wanted to justify this one here for you, if I could, real quick. Again, I'm going to try and draw a triangle that has a secant, an angle here that has a secant of x. So what do I need to do? I think that, right? Does that angle have a secant of x? So this over here is root x squared minus 1, right? So what's the tangent of the angle that has a secant of x? I think it's root x squared minus 1. And then, like I said, this doesn't equal x, and I don't really want to get into it, so, but just trust me on that one. Okay. 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 So, you know, that's a little derivation of secant inverse. That's left for you as a exercise. Try doing tangent. That's not too bad. I did secant because it's a little trickier, but implicit differentiation, though, right? That's how you get those. Okay, let's see if we can do at least one example or two before we leave, before the bell hits. Okay, so you got these. They're in a box, so you know there they are. They're in a box. You know those 6 now, hopefully. Okay, hopefully you have them close at hand. At some point you'll have them memorized, but right now you might need to refer back to them. So let's find the inverse sine of t. We got here. Let's find dy dt. So what is dy dt? Symbolically, 1 over the square root of t. Oh yeah, I'm working with a t. And then plug in 1/2 and tell me what you get. Sorry, a little carried away with my slashes. Yeah, what do we get? 1 over the square root of 1 minus 1/4, I guess. So that's 1 over square root of 3/4, which is 1 over square root of 3 divided by 2, which is 2 over root 3. Does that work? Be a nice way to say that. And then cosine inverse. How do we do cosine again? Cosine inverse? Yeah, it's just the opposite of the derivative we've just been talking about. So what do we get? Negative the square root of 1 over the square root of 1 minus x squared squared. Oh wait. Times 2x, right? So we need to clean that up a little bit, maybe. Not much. Actually, let's just write it. It's negative 2x over the square root of 1 minus x to the 4th. Yeah? Not too bad? I don't know how else to simplify that necessarily. I don't know what more we could do. Do I have more? Of course I do. Did you need that again? Rosa, did you need that? Or whoever else? Okay. By the way, I should maybe make a comment about those last ones. When are they defined? If I can go back. When is this expression even defined? I can ask about 1/2, maybe. But yeah, it only works for -1 to 1. Does that make sense? The derivative only works for -1 to 1? Well, what about the original function? It only works for -1 to 1 too. So let's just to be clear, there's no problem there at all, right? So y prime here is equal to what? What is it? 1 over, you can look at your page if you like, 1 plus x squared, or in this case, root x squared, right? So that'll be 1 over 1 plus x squared. I guess we should say for positive x, right? Or non-negative x. Just because of this, right? It's certainly true that, I mean, the original function doesn't even exist, does it, for negative numbers? Whatever, yeah, you know. You're right. I'm thinking the bell's gonna ring any second, and we're not gonna do this one, but we can maybe do this one. Where's that meeting? Just one more example, guys. Go to homeroom, guys. Oh, we didn't do that yet. What is that? X to the negative 1/2? Yeah, chain rule. The homework is not going to be talked about or checked until Thursday, I guess, right? It's the next one on the homework. It's that on the first slide. It's book homework. 3. But tomorrow we'll take a quiz. Wednesday of PSAT. So. Okay. Oh, you just did it? Bye, guys. Sure, I will. I have. Yeah, and it's just a quick question. That'd be fine. Yeah. I have a staff meeting after this, but but that's okay. If I'm running around like a chicken with my head cut off after school, you can either or someone else can get the brownies and from the top of they're on top of the fridge. Okay. I'll try and get them too, but I have like two or three kids coming after school for random things. So. Thank you. Thank you.
Thank you. Kelly.
Hey, what's going on?
Thanks, Mr. Chase.
Yeah.
See you later, guys.
What?
Hey, Peter.